A very good day to the honorable panels. My name is Muhammad Putra Danial bin Shahrulnaz Norhazli, and today I will present my research on YOLO, Best Intelligent Interpretation of Ground Penetrating Radar GPR data for underground power cable detection. Supervised by Dr. Mimi Binti Ghazali, this study develops an NNI-driven pipeline to accurately pinpoint the buried power cables in challenging tropical soil conditions. Let's start with the background of study. Moving on to the background of study, which is based on three main pillars. First, prerequisite for infrastructure safety. Accurate utility identification is critical to prevent accidental power cable strikes during excavation and maintenance. Second, industry standard non-destructive testing. GPR is the global benchmark for the task because it effectively records electromagnetic differences caused by buried assets as validated by Zhao et al. 2025. Third, the interpretation bottleneck. However, raw GPR data is hard to read. Traditional manual interpretation is labor-intensive, highly subjective, and relies heavily on the operator's expertise to separate fan cable signs from soil noise. This bottleneck is why our study aims to automate this process using deep learning. Now we continue to the problem statement. Our research addressed a chain of three critical challenges in utility mapping. First, environmental noise and subjectivity. High moisture tropical soils scatter radar signals, producing weak and broken hyperbolic shapes. This makes manual interpretation highly subjective and prone to human error, risking dangerous utility strikes. Second, the localization limits of standard CNN. Standard network only classified if a cable exists in a scan. They fail to provide the precise spatial bounding box coordinates that fill excavation crews' absolute need. Third, the target size and architectural dilemma. Legacy models like YOLO V5 struggle to detect small diameter cables in a damp soil, while newer single-stage detectors offer real-time speed. Two-stage detectors like RCNN traditionally offer better pattern accuracy. Currently, there is a strict research gap as the latest YOLO V11 has not been empirically benchmarked against RCNN in highly attenuating tropical soils. This study bridged that exact gap. To address the challenge mentioned in our problem statement, this study is guided by three core research objectives. First, to identify the characteristic hyperbolic signatures of underground power cables and apply digital signal enhancement techniques. Second, to develop and optimize an automatic detection model using YOLO V11 architecture. This objective focuses on achieving high precision spatial localization for small diameter power cables, utilizing a traditional CNN framework, especially RCNN, as our benchmark baseline. The third, to comprehensively evaluate the performance of our proposed framework. We will measure and compare both the detection accuracy and real-time processing speed of YOLO V11 by benchmarking it directly against the RCNN model. Together, these three objectives provide a complete pipeline from raw data enhancements to an optimized development model. For data acquisition, for the fieldwork, we conduct GPR surveys at the UTMR campus. We use high-frequency antennas specifically to capture the high resolution reflections needed for small diameter power cable, all within the challenging high moisture soil condition, Malaysia. For synthetic data generation using GPR Max, to overcome data scarcity, we use the GPR Max to generate synthetic radiograms. Using FDTD modeling, we simulated thousands of hyperbolic signatures across various depth and soil dielectrics, ensuring our air model has robust foundation before being tested on the real-world data. In pre-processing section, the raw GPR data is notoriously noisy. We apply a pre-processing pipeline involving background removal to eliminate surface clutter and time varying gain to amplify the faint reflections from the same cables, making the target clearly visible for the AI imaging. In data annotations, we use a label studio. We focus our annotations tightly on the hyperbole apex, as this represents the exact spatial coordinates of the cables. This ensures our model learns to localize, not just classify the target. During the training phase, we benchmarked the state-of-the-art YOLO V11 against the fast RCNN framework. Both models were trained using a workstation. By transfer learning, balancing single-stage speeds against two-stage architectural precision. Finally, we validate our models using unseen field data. We evaluate success based on mean average precision for localization accuracy and inference speed (FPS) to determine if the framework is fast enough for real-time development of site. Now, presenting the quantitative performance metric across the different dataset sizes. First, on detection accuracy, YOLO V11 consistently achieved a flawless 1.0 precision across all dataset sizes. It peaked at 200 images, yielding an exceptional 0.990, mean average precision at 0.5, and an F1 score on 0.95. Conversely, while fast RCNN managed to reduce its average loss, its average precision degraded severely from 98.3% down to 74.6% as the dataset scaled up to 400 images. Second, on computational efficiency, YOLO V11 proved to be substantially faster. At 400 images, YOLO V11's complete training in just 5.24 hours, whereas fast RCNN bottlenecked aggressively at 14.5 hours, nearly 3 times longer. In conclusion, this data confirmed that YOLO V11 successfully breaks the architectural trade-off. It delivers superior localization precision while drastically reducing computational overhead, making it ideal for real-time field development. To conclude our presentation, first, as a preliminary conclusions, although the research is still an ongoing study, our early finding provides strong empirical evidence. The current data clearly demonstrates that YOLO V11 delivers superior localization precision while drastically cutting training time compared to fast RCNN, proving that our framework is highly viable. Second, as a recommendation for future research, since this pipeline established as a solid foundation, future researchers can expand this work in 3 main directions. They can explore multi-sensor data fusion, perhaps combine GPR with electromagnetic locators to make detection even more foolproof. Number 2, future studies can scale up the datasets to include a wider variety of Malaysian tropical soil profile to test model limits. And finally, the other researchers can focus on edge AI development, compressing our optimized YOLO V11 model so it can be embedded into mobile apps or AR device for real-time use by excavation crew on site. Thank you very much, and that's all from me.